I know I have taken a lot of time describing these, but it is fairly deliberate because this is a good time to establish these ideas in our mind and not find them very alien if they appear or when they appear later in this course. And this is just, it seems, about the 0th order term of the Taylor expansion. We have gone a little beyond that in talking about all this, but be that as it may, all this comes about from orienting our say visual ideas about these pulses to being thinking about it in terms of shapes of electric fields and not just a plain vanilla Gaussian like envelope and say that's all there is to it. There is a lot underneath the canopy. Yeah. So your question.
Is that new knot that you added, is it same across different nodes? Does it have to be same across different nodes? New Q is equal to new knot plus new Q.
Yeah. That's the whole spectrum having one offset.
But due to the system, it's not necessarily that the whole spectrum has to have the same offset.
Well, nu naught could vary in time. It could have a slow variation in time too. It can. Nu naught also can vary in time. So the way to think about that is this: is the following. You have here a distribution. You recall our picture of the cavity modes, a measurement which I showed you in black and white earlier. This is now a distribution which has 2 degrees, at least 2 degrees of freedom, as we could see. One is the position of its, you can say, center of mass, and this is the other degree of freedom, the spacing between any 2 teeth of the comb. So the whole spectrum can move. What we are saying, that what we mean by saying that nu naught can vary in time is that the center of mass can move around. So if I were to plot this in time, maybe the center of mass did that as a function of time. The comb was moving around. The other is if the comb can breathe, right? The spacing between the other effect that can happen to the comb is that basically its 2 modes, the FSR can also fluctuate in time. So these two can, and what you are saying, I mean, in that sense, well, the FSR, if you take a snapshot of the spectrum at any instant in time, you will find it has a nu naught, it has a nu FSR. But these things can drift in time rather than vary. I would say that for a control system, the laser that produces fairly reproducible pulses, these will drift in time. Yeah, it's like if I may say, being in a very nice, the nicer your car on the road, nicer the road, the lesser will be these little things, but there would still be a little bit of jiggling around, right. So rocking, if you wish, slight rocking of these things. So for a very good laser, you can control all this and nudge the system back to a very well defined central nu naught frequency or nu FSR, right. So but therein lies, and since we are in discussion mode, therein lies another remarkable thing. If you can read it, if you were to spend substantial time and effort in doing this, you not only achieved something in the frequency domain. Remember that if this combs interleave of the comb frequencies can be controlled very well, and you could control also the offset very well. What did you just do? What did you just do? What did you just do? You defined a petahertz frequency extremely well. You see? You made a frequency standard for all of mankind's and even aliens, as Max Planck said that. Right? Because Nu FSR is some refractive index of a medium times C by cavity length. That is all. And you define the frequency very well, and that is connected to a fundamental constant. That is the beauty of it, you see. That is also the idea of current modern SI units and metrology. It is connected to a fundamental constant, and you have defined these frequency extremely well. So, let us flip this around a bit and say that if I can nudge the offset frequency and whatever to be kilohertz, keep within a kilohertz of a central value for a long time, and I maintain that, then I am maintaining a optical frequency standard with a precision of 10 to the minus 12 to 13, you see. But it needn't be even that. If you can, it so turns out that it's okay to do this even up to a mega, this offset could also be, if you are able to control this within some megahertz, you have again megahertz frequency standards. So, you chain these two guys together, you tie them together and say, now you both work coherently and in sync, and the megahertz frequency standards precision could be sub kilohertz, let us say 100 hertz. You build a frequency chain that can go from very low frequencies to a petahertz, and so you have defined then a petahertz frequency very well. And I cannot resist my temptation in saying that if we did this, what this literally means is that you have so many optical cycles, you somehow got a resonator where this wave train, you manage to make a wave train like this, which has that many cycles, 10 to the 13 or 14 cycles unbroken, an unbroken wave, unbroken in phase for 10 to the 13 cycles or so, which is really impressive, and that is the level of timekeeping possible today. But there are intermediates. We have petahertz, we also have other definitions like a cesium clock and so on. And just so happens that yesterday I visited the National Physical Lab, where they maintain time for the entire nation and maybe some other nations too. Standards work by replication, right? By replication of primary standards and secondary standards and so on. So that's the job, but that is done in the Indian context currently by a hydrogen maser. So is it any surprise? It's again hydrogen microwave laser or maser, or microwave amplification by stimulated emission of radiation by hydrogen maser. So the time and frequency domains are really interlinked. So this course we are harping so much on attosecond time scales, femtosecond time scales, and see how it is interlinked to this. And I mean, again, I don't consider it a digression. I think this is what courses should do. This is done for petahertz frequencies, 10 to the 14 to 15 hertz. I mean, 0.1 to 1 petahertz, be a little forgiving. Don't say that 0.1 petahertz is only 100 terahertz and not 1 petahertz. Allow that for a change, but nothing stops us from carrying forward these ideas to 10 to the 17 to 18 hertz and making these what we now call these frequencies combs in the optical domain to the extreme ultraviolet domain. That's so. What is after peta? Is it exahertz, right? Maybe we should call it exahertz domain. For doing this in doing these in the petahertz optical frequency domain, of course, or for technology, science, physics and technology in this of these combs in the petahertz domain was the reason for the Nobel Prize in Physics in 2005 to Jean Hall and Ted Hansch. So, and they are probably not Professor Hall, but Professor Hansch, and but also younger colleagues, because Professor Hansch today is an octogenarian but a very active scientist still, whom I had the pleasure of meeting once, at least once, or maybe more than once. Right, okay, I don't want to write ages. So the point being that they are pushing this, the same sort of philosophy or idea or theme to the extreme ultraviolet domains, to have extreme ultraviolet frequency combs, and push therefore the definition of 1 second to 18 digits of precision, close to 18 digits of precision. Today we have 14 to 15 digits. It's the most precisely measured quantity. You can either you call it a time or a frequency. They are really just the inverse. So you define a frequency to 14 digits, okay, and ergo the second or the or unit of time. The idea is to push this to 17 or 18 digits too. It's just a passion for precision at play. So all that really rests on this, and really in some sense, if you see, it's just the frequency domain description of the pulse, and sometimes this innocent, even this little innocent zeroth order term has meaning and pertinence. In this case, if you examine it sort of closely enough and its implications, you really don't need a great, tremendous physical acumen or whatever. If you just do some free thinking, many of these ideas could well be points of discussion. So I certainly encourage you to adapt something like that in a peer-to-peer mode, and it could be material for tutorials. So maybe today we had quite a tutorial in the name of a lecture as well, but that's fine.